Right, next person in this track talking is me. Okay, I'm Robert. So, what I'm going to talk about is give an overview of what the beam looks like internally, or parts of what the beam looks like internally, to give you some feel of what's going on in there. So this is the Hitchhiker's tour of the beam, right? It's not a guide, it's not deep enough to be a guide, but it's a tour. And the first thing, of course, to try and describe is, what is the beam? What do I mean by the beam? What's it doing, right? And, well, it's many things. It's many different parts of it. And one thing is, it's a virtual machine for running Erlang. That's really what it is internally. That's the whole goal of it. It's also an interface to the outside world. I mean, there'd be no point in running Erlang if you couldn't talk with the outside world. And it has a number of ways of, well, basically Erlang has two ways of talking with the outside world. It's got the concept of ports, which look like processors, and nifs, which look like function calls. So the beam must support ports and nifs. And it does contain a bunch of useful built-in functions, so-called BIFs, the varying things there. And I'm not going to talk about describing Erlang, but I will say a few things about the Erlang because it affects how the beam works and what the beam is supposed to do. And these are the properties of the Erlang system. So an Erlang system, it depends on, it's defined to contain lightweight massive concurrency. It uses asynchronous communications, asynchronous message passing. It needs process isolation. So, well, the concurrency is based on processes, and it needs process isolation to be able to do the error handling, to be able to build proper fault-tolerant systems. It needs to be able to do continuous evolution of the system while it's running, which in this case it needs to handle code loading dynamically. And it is soft real-time, or supposed to be soft real-time. So you have the concept of time and timeouts. It does not guarantee it will always be able to fulfill them. So the real-time people would not don't call Erlang real-time, because it doesn't guarantee that. And these properties the beam has to support. If it can't do that, it's not implementing Erlang. And it has to be able to do this efficiently, because when we write Erlang code, we assume this. We assume we can start lots of processes, and it's cheap to do that. We assume we can send messages and it doesn't cost too much, etc. So it just has to do it. It has a few other properties of the language as well. None of these are especially specific to Erlang, quite general type of things. So in common, you'll find in other languages as well. So yes, there's immutable data. And if the beam can support immutable data properly, that's fine. It makes it more efficient. We have pattern matching. And if you look through Erlang, pattern matching is ubiquitous. So to make efficient code, there should be good support for pattern matching, for doing pattern matching in the machine. And it's a functional language, which means we call functions all the time, so function calls should be relatively efficient. Now, none of these things are specific to Erlang. They're quite common things. The other things I was talking about, the Erlang system, some of them are quite specific to Erlang, and you won't find them in other environments as well. In many ways, the other set, if you just pop back, they are more operating system-like. They're more common type properties of operating systems rather than languages. So how do we do this? So we end up, to run Erlang, the beam needs to support all of this, at least. So we're going to look at a few things about the beam. We're going to look at a concept called schedulers, look at processes, a bit about memory management, message passing, a bit about multi-core, and a few other things as well as we go. And we're not going to really dive deep into anything. We're just going to brush over the top of things. The basic, well, what you might say, the building stone of the Erlang system is a scheduler. Okay. And It is, in one sense, it's a semi-autonomous small virtual machine running the beam. Okay, so it tries to operate as independently as possible of other schedulers in the system. Of course it can't, because you're running the same one Erlang system, and of course they will be talking with each other and so on, but it tries to do as much work as possible independently. And by default, well, the system starts up one Erlang scheduler in a separate VM thread. So you have one VM thread per scheduler the system is running. And it says it tries to run as separately as possible. It, for example, contains its own run queue. So it contains its own set of processes it's trying to manage and run and things like this for it. By default, the Erlang system will start one VM thread, one scheduler per core in the machine. But you can control that. You can set how many schedulers you want. You can lock them or bind them to cores and this type of thing as well if you want to. Or you can just let the system do it for you. I think we saw in the previous talk, sometimes you don't want to let the system do it for you. You can, for example, if you want to start multiple schedulers per core. You can probably find use cases where that's reasonable to do. So the machine, the beam, tries to spread the Erlang tasks or processes over the multiple schedulers. And it does try and do a bit of balancing work to try and keep the schedulers reasonably well balanced. And every period, it's about 40K reductions. Reduction in this case is a function call. The name reduction comes from the bad old days when it was implemented in Prolog. And Prolog doesn't do function calls, it does reductions. And that name is stuck. Literally 25 years it's stuck. I think probably about 23 years since we actually did a reduction in the system at all. But anyway, it's still there. And what happens is that the schedules will run separately, and the first scheduler that reaches this limit, which I think is about 40K reductions now, that scheduler will decide, I'm the master. And it will tell the other schedulers it's the master, and it will go out and try and do some balancing and try and optimize the workload between the schedulers and move things around if possible. Just try and detect things that aren't working and stuff like this. And will actually suspend unneeded schedulers. If it finds there's not enough work for all of them, it can actually suspend the schedule as it goes. It does its work by putting things on schedulers' run queues. So if it wants a scheduler to take a process, it will tell the scheduler, it will put a job on that scheduler's run queue now to take over a process or do things. So very rarely actually synchronously tells the scheduler anything. It works through the run queue, which keeps down the need for synchronization between the scheduler. And then when the master's done, it tries to balance, it stops, it goes back to being a normal scheduler, and you keep on going until the next time someone hits this limit and it takes over the work of being a master scheduler. So this master will move around. It's not in any way defined as, not one scheduler is defined as being the master. So one of the main things a scheduler does, of course, is scheduling processes, Erlang processes. And an Erlang process can be in a number of different states. So it can be running, actually doing work. It can be runnable. So it can be in the run queue. It just it's just not its turn to run for the moment. Or it can be waiting. So it can be waiting for a message. It's in a receive. It hasn't got a message which matches. It just sits there waiting. Or it can be exiting. It's been killed or it's dying, and it's on the process of going down. So in the same way here, that when a process is killed, it's put on the run queue with information that the system is now to kill this process. And then when the scheduler gets to its turn in the run queue, it will then kill the process. It can be garbage collecting. In the same way, while it's garbage collecting, it's in a garbage collecting state and doing stuff. Or it can be suspended. You can actually explicitly suspend a process to stop it from running and then resume it afterwards. There are calls in the system to do that. So the process can be in these states. And again, each scheduler has its own run queue. When scheduling processes, The important thing to remember is that when a process is waiting for a message, it's suspended. It's in a non-busy wait. So it's not sitting there polling or anything like this. It's just sitting there waiting, and when a message is sent to that process, then it's scheduled and put in the run queue. So it's perfectly acceptable. It works, no trouble, to have lots of processes just sitting there waiting for messages. They don't cost execution time until actually someone sends them a message. So there's no problem in having lots of processes monitoring, suspending, waiting for doing things. It costs memory, but that's it. It does not cost CPU time to do that. And when a message arrives, the process becomes runnable. It's put in the run queue, and when it becomes its turn to run, it will try and match that message against its receive statement, and either it works and it'll keep on going, or it's not a message it wants, and it'll become suspended again and go waiting again. And sit and wait for the next message to do that. Running processes do not block a scheduler. I mean, what I mean here is they don't take over the whole scheduler. And that's done by, well, when a message arrives and it has to wait for a message to become suspended, this next process come in, and while a process is running, it will be rescheduled. After, I think it's 2,000 reductions, that process will be rescheduled and let the next process in the run queue come in. So you cannot block an Erlang scheduler by having a process that just continually executes code. So that was a bit about scheduling and processes. Memory. There are a number of separate memory areas, different types of memory used for different uses in the system. Some of them, for these, there are actually more. So we have process heaps. So each process has its own heap, which it manages by itself. ETS tables, term storage, they're in a separate area. They're not in any process, they're outside the process area. We have the atom table. We have the large binary space. I think it might have another name, but I think that sounds, it might call something different. But large binaries that are bigger than 64 bytes, exist outside the process areas. There's space for code, of course. There's space for timers, and there are other things as well. Well, I'm not going to go through all of these. Just do some of them. The easiest one is the atom table. So all atoms are global objects. And there's a global atom table containing all the atoms. That means handling atoms is fast. Comparing atoms is fast. You're basically just comparing the index into the atom table, if you want to do an equality comparison. Which means there's really never any use for not using atoms as a tag. If you put an integer in there, it will not go faster, because then you're comparing the integer value. When you're comparing atoms, you're comparing the index in the atom table. It's the same thing. But atoms are never deleted. So once you put an atom in the table, it's there forever. Which means that you can fill the atom table. And when you do fill the atom table, you'll crash the system. And that means that you should be careful of dynamically creating atoms in your application. So you shouldn't do things like using atoms for unique identifiers or stuff like that, because then you will fill the atom table and you will crash the system. The atom table is big enough, so by default that will not happen. I think the default size is 1 million atoms or something like that. And you cannot write code that contains 1 million atoms, different atoms. You just can't do that. So just through normal code usage and stuff like this, you will not fill the atom table. But if you dynamically create atoms while your application is running, you will eventually. It's just a thing to be careful of. There are two calls. There's list to existing atom and list to binary atom, or binary to existing atom, which will only create the atom if it already exists, which gives you some form of control over that, for example. But again, you don't use atoms for unique stuff. They're not unique. That's also the problem. So if I create an atom with a funny name, someone else can create that atom with the same funny name, and we've suddenly got the same atom. So they're not unique anyway. So that's the atom table. We have the large binary space. So as I said, binaries bigger than 64 bytes aren't stored in a process, they're stored in a separate memory area, which is very nice for some things. It means when I'm sending these large binaries around, I'm just sending references, just sending pointers into the binary space for them. So I'm not copying large binaries, which means you can write applications where you're sending large binaries along processes and between processes and processing them, because you're just not copying them. So you can actually do video, stream video through Erlang by Erlang processes, sending them through Erlang processes binaries, which is very nice. The downside is that it can take a long time for the system to detect that a binary in the large binary space is no longer being used. Basically, the way the system works is that you reference count the binary for every process that the binaries pass through. And it can't decrement that counter for a process until the process has been garbage collected. That's the only way the system knows that this process is no longer referencing the binary after it's done a process garbage collection. And actually, a full garbage collection, we'll see what that means in a moment. So in the worst case, you can be creating lots of large binaries. You'll be streaming them through processes, and maybe some process or some processes very seldom do garbage collection, which means it can take a long time for a binary to actually be reclaimed. The space for the binary to be reclaimed, that actually can crash the system. So I was talking to one guy who he sort of ran into the pathological case. So he started 2 Erlang nodes, and he was trying to see how fast you could send binaries between the nodes, just to work out the speed of communication between the nodes. And on one node, he created a binary about 1 megabyte big. Then he spawned off a few thousand processes on that node, which then sent the binary to a few thousand processes on the other node, and just sent them across. And after the processes didn't do anything, they just accepted the binary. He just kept on so he could measure how fast it went. And after a while, the second node crashed. So what was happening is the binaries were being sent over. Every time they were sent over, it created a new binary. And there were large binaries, they went to large binary space. They were sent to the process. The process didn't do anything, these receiving processes. And it took a long time before they garbage collected and memory ran out. And so the whole system crashed. Now, unfortunately, it was running on the Mac, so the crash dump, or the dumping of the crash dump, crashed as well, so he didn't get any information out of it at all. So there wasn't even a crash dump at the end. And after a bit of working out, we worked out this was what was happening. We're getting all these binaries sent over, they were filling up the system, there was no garbage collection. There was no garbage collection being done in the system that crashed it. So he just put a call to the garbage collector in the loops, and suddenly the whole problem went away. It went much slower, of course, but the problem went away. So that's a real problem, and it can happen. The ETS tables. So, ETS table, data for ETS tables outside all processes. And that's one of the goals of why you have ETS tables. So one of the limitations in the Erlang implementation with having separate process heaps is that you don't want to have really big processes, because that affects the garbage collection time. So you want ETS tables outside processes so you can make truly big ETS tables. So you can have ETS tables of gigabytes of data in there. They are not implicitly garbage collected. What I mean there is that an ETS table is not removed until you explicitly delete it. So even if no one references it, it's still there. It's like a process. A process that does not go away until you explicitly kill it. Right? An ETS table does not go away until you explicitly delete it. But of course, the data in the ETS table is garbage collected. So if I delete an element of the ETS table, the space it used will be reclaimed, of course, but the ETS table itself does not go away until I kill it. A problem with this is that every time you access an ETS table, you are copying data from between your process down to the ETS table and back again. There is no way around this. That means accessing large tables or scanning large tables can mean you do a lot of copying. That's why, for example, you've got these match and select operations, which allow you to do more intelligent scanning and limit the number of things you actually copy into your process. Do that. That's also something to be aware of. But they can store large amounts of data. I mean, as I said, literally you have gigabyte ETS tables. So that which was one of the reasons for having it, for creating edge tables. The other reason that you wanted more constant time access to edge tables, which they do provide. Yeah, there's a question.
So are binaries copied into, or is the pointer copied into the edge table? So if you have a large
I would assume if it's a large binary, it's in the large binary space. But I honestly don't know. The question was, if I got a reference in an edge table to a binary, is the binary copied into the edge table or not? And I said, I don't know.
It's in the binary space.
It's in the binary space.
So you're just copying the pointer.
Yeah.
Not
Okay.
copying the
Yeah.
binary.
Yeah. That's what I would expect. But sometimes, yeah. Yeah. One thing to remember with edge tables is, in some ways, they're process-like. So they're more or less linked to the process that created them. So if that process dies, the edge table's deleted, which can cause a bit of trouble if you're not expecting it. Process heaps. Yeah, each process has a separate heap. So all data to a process is local to that process, and it's in the process heap. You can, well, by default, when you create a process, it starts off tiny. It's somewhere about between 200 and 300 words big, the process heap for it. It's the minimal size of the process. And as you grow, the data grows, you're garbage collecting it, and you're growing this heap as you go along and so on. You can give options to create a process with a larger minimal heap, which can be quite reasonable if you know your process is going to grow, become big. You can do that at start and say this process minimal heap is going to be bigger than this. That can optimize quite a lot. You can do it at a per process level or for the whole system. You can say for the whole system, no process is going to be less than 1 mega words or something like this. Of course, you have to be careful. That means you can't create that many processes because suddenly all the processes are very big and you don't have memory space for that, so it's a trade-off. Or you can do it as at a per process level. Say, I'm creating this process, I want the minimal heap size to be this because I know it's going to get big. I don't want to just get around it at the beginning. This means that sending messages between processes means copying the data. There are no references from one process to another process. Each process, the data in the process is completely separate and isolated, which is what you need for the error handling. So one of the main fundamental requirements for error handling is that a process can crash and not affect other processes, not ruin the system for other processes. And to do that, you have to make sure you don't have references between processes, or uncontrolled references at least. And the current system does that by, as I've said, having a separate process heap per process. Note one thing. This is not required by the language. The language doesn't say how you implement it. The language says you have process isolation. The language says you can crash one process and that won't affect the data in another process. Seeing you have immutable data, you can share data between processes and they can crash separately and they won't affect each other, seeing you have immutable data. So this property of having separate process heaps is in one sense sort of an implementation detail. Though it's a very fundamental one and affects a lot of things. So for example, if we didn't have separate process heaps, we wouldn't need to copy messages when we send them. We wouldn't need a separate area for edge tables, and a lot of other things like this. But we do have it, and there are good reasons for doing it.
There's no maximum heap size that you can set.
No, there is no maximum heap size per process you can set. The process grabs everything it can until there's nothing left and the whole system crashes. So you can set the minimum size, but you can't set the maximum size for it. But then you get the question, if we now got separate process heaps, and sending a message means copying the data, isn't all that copying very inefficient, right? Every time I'm sending something, I'm building the data structure in one process and copying it over to the next process and building it there, and so on. Isn't that very efficient? Well, yes, it is, sort of. Perhaps, maybe, right? But there's a but, of course. There's always a but. One thing it does do which is also fundamental in the system, it does enormously help you garbage collect in the processes, garbage collect in the system. Because it means I can garbage collect one process at a time. I don't have to do anything else with the rest of the system while I'm garbage collecting my process. I don't have to synchronize with it. It's not sharing data. I don't have to do any extra work for the rest of the system to allow my process to garbage collect its data separately. And getting rid of synchronization and locks is a big, big, big win, right? If you were here for the last presentation, when the guy from Concurrix was, Alexander from Concurrix was talking, the problems they had with that type of problem, or the problems they discovered with that, shows that anything you can do to save synchronization is a win. And having separate process heaps allows you not to do that, and it's a big win. It also means that every time you do a garbage collection, you can you can garbage collect each process separately. I can do a stop and copy garbage collection on that process. So I don't have to do a real-time garbage collection or anything like this in it, because the process heap is so small that the garbage collection time per process is so small that it still keeps the real-timeness of the system. If I was doing, say, a whole heap garbage collection, that can take a long time. At least from an Erlang point of view, a long time. Then I would have to do a lot of extra work to make sure that the garbage collection does not interfere with the system, and that's effort. To do that seriously, it is. And it's not always certain you actually gain anything by it, because the garbage collection becomes more inefficient, so it takes longer time, and most of the time you save by not having to copy data, you lose it in the garbage collection.
I have a question related to garbage collection
Yeah.
and binary data. And I took some part of the binary data and handed it over to the other process. And then the process called garbage collection at that time, and the original process is terminated. And then the partial data, the original binary data is garbage collected over.
Okay, here was the question here about we're sending a binary from one process to another.
But I sent only a subset of the partial data.
Yeah.
The next talk will.
The next, yeah, you'll explain that much better than I, more detail than I do. That takes up this problem. Yes, there is a problem there. Yes, there is a solution, but yes, you have to know what you're doing to use the solution. I think that's the best. I'll leave it to Eric to take care of that. The next talk, yeah, yes. It's a known problem, put it this way. But yeah, the garbage, and also the garbage collector becomes much simpler. And that is not something to laugh at. An error in the garbage collector, typically you see it a few garbage collections later, when some pointer is pointing in the wrong place, and you have absolutely no idea what happened. Right? You see the effect of something. It could have happened one, two, many garbage collections earlier. You have absolutely no idea. It just crashes because the pointer reference is wrong. So keeping the garbage collector simpler is in itself a big win. And as I mentioned, having a real-time collector in one heap doesn't always give you anything. I myself did some experiments, only single core, so it was easier, of having a single heap and having an interactive collector on one heap in the whole system. It was interactive enough, so that we had the soft real-timeness of the language, and it made message passing really fast. I could send big messages around the system as fast as anything. Put a real application on it, and there was basically no difference in speed doing that. So yes, I could have faster sending messages, but the collector became more inefficient. There was just no way around that as well. So the result was, the net result was about the same speed, which is very depressing. Well, I'd done a lot of work, but it was very good. It was very good. It was doing its job properly too. And yeah, the benchmark went fine, but the application, a few percent, it's not worth the effort. And it is much more difficult. And some of the bugs were really hard to find. So the garbage collector at the end of the system, at a per process level, it's a copying up. This is pretty standard fare. Okay, seeing you do it this way, you can use most of the standard technologies for doing garbage collection on it. So per process, it's a copying garbage collection, which is very nice. It means you're copying the live data and just leaving all the dead stuff there. which is very good in this type of language because you're creating a lot of data and most of it becomes old very quickly. So if you can just look at the live data, it's actually a lot less work. It's also a generational collector, which is based on the heuristic that most data dies young. So if I just collect all the young stuff very often, I'll get most of my garbage, I'll find most of my garbage in that. And I just save all the stuff that's been done. So that's what's done, generally called the new space. And after a while, after a number of collections, any data still alive is passed down into the old space. And that is a very good heuristic for this type of language. So it means that not much data unnecessarily ends up in the old heap. Of course, you will have to garbage collect the old heap eventually as well. And there will be garbage in there, which means you have to collect the whole system, the whole process. But generally that will be quite fast anyway. So that's a very nice heuristic about it. You can do a bit of tuning to process heaps. Again, this is the type of stuff that's, you set the tuning and sometimes these things go much faster, you change the value slightly and suddenly it's going much slower. But what you can do is you can set the minimum heap size, I mentioned this before, and that means that the process heap will never go under that size. Which is fine if your process, you know your process is going to become big occasionally, you can set this. It will just make it more efficient when the process heap grows and shrinks. But you pay the price in memory. So if you choose it for the right processes, it's a big win. If you choose it in the wrong processes, you're wasting memory. You can control how often the garbage collector does one of these full sweeps. How often it does one of the generational collections of the new space and how often it does a full sweep. You can control that. When to do it, it is black magic in a sense. You can set the parameters after how many calls and sometimes things will go faster, you change the value, sometimes it goes slower. It forces the collection more often. Okay, so it means you're doing more garbage collection, but you're reclaiming memory faster. And so it uses less memory. And the big win here, it reclaims large binaries faster. So if you think you've got a large binary problem, maybe a solution would be to turn on, lower the full sweep after for a process, or doing explicit garbage collection for a process, just to get back your little binaries faster. But the collection is less efficient because you're scanning a lot of stuff which in one sense is unnecessary to do, doing more work than necessary. But sometimes it'll give you a win. This is just a few interesting things about the system. We have something called the async thread pool. And that's a collection of other threads. Threads, operating system threads that the Erlang system manages for you to do stuff. Right? And it's based around the problem that file I/O can be problematic. It takes time. I mean, yes, disks are much faster, but compared to everything else going on in the system, reading or writing data from the system from a file takes a long time. And you definitely don't want to block a scheduler, a whole scheduler, while I'm reading a few bytes from a file. Because blocking a scheduler, that does affect your real timeness of your application. Because while that scheduler is blocked, it can't do anything else. Anything else that might be vulnerable in that scheduler will just stay there because the schedule is blocked. It can't do anything. So using the async thread pool, that allows the system to move file I/O operations out of the scheduler into other threads, into other operating system threads, and put the work there and allow the blocking to occur in those threads while the scheduler keeps on going. So it just schedules the work in another thread and keeps on going, which is nice. It keeps the real timeness of the system. Up to R15, the system did not by default start any async threads. There was a +A switch in the emulator which allowed you to set the number of them. Now from R16, I think it's 10 threads by default it uses to do this. So it just starts up these extra operating system threads it can use for doing the asynchronous operations. And
are there any known caveats from
Any known,
Caveats.
any known caveats for it? Well, you're creating more, well, I mean, you're creating more threads, of course, in the system, which means you're doing more context switching in the threads and so on in the system. So nothing's free. So you have to choose what you want to do. I mean, you could turn off completely and then just do everything as blocking operations in the scheduler. Take your pick. There's a Swedish saying says plague or cholera, right? Pick your disease, right? Yeah. But if you've created them, or if they're created, the file I/O actually uses them by default. And you can, if you're writing linked import drivers, you can write your linked import drivers to use them as well, if they're there. A bit of testing, you can test if I have them, I can use them. But the iNet driver does not use them, because apparently it's not necessary, because the socket interface, the iNet interface, is generic enough on all systems so that you can do non-blocking operations on them without having to start going to async threads. So the system can do non-blocking operations on the iNet stuff. So it doesn't need to do them.
What
So
if there are 10 cores in a machine, and it means that there are 10 schedulers, right?
yeah.
They are separate threads, and if I put 8 plus 8, 10, then what does it mean?
Okay. The question was, if you're running on 10 cores, by default you'll get 10 schedulers. What does it mean if I do plus 8, 10? That means you'll start 10 threads more. Yeah, so you'll start extra threads for doing it on file I/O stuff. And I mean, how many you need, of course, depends how much file I/O you're doing. So if you're not doing much file stuff, you don't need them. If you're doing a lot of file stuff, you do. Yeah.
By file, you mean reading file or like socket or, I mean, Linux, everything is a file, right? So
Disk.
when you say file,
Disk
you mean
files.
File system file?
Yeah, file system files, the disk files, I'll put it this way, reading from the disk. Other Linux file systems, things, will be fast or slow depending on what they're talking about. I'm reading stuff from the disk is slow, comparatively. Yes, it's much faster these days than it used to be, but compared to what you do in the operating system, it's much slower. And if you're doing a lot of file operations, then it might be a big win to have many async threads. I don't know if there's anyone from Basho here.
Oh, yeah.
You use a lot of, Basho, I know, uses a lot of async threads because they're doing a lot of file operations.
I don't remember what we said plus A to nowadays.
Someone said you said plus A to 1024, but I don't know, that was just someone who said it, wasn't someone from you, so I can't verify that. But it's a big number anyway. It's much bigger than 10. You're doing your own threads now?
Well, we do, well, with Level, we do a worker pool,
Yeah.
but, and do all the work over there, but I don't know enough to say what we said in VMRs. Top of my head, let's say.
But they're there if
But
you
I
need.
can confirm we do use the disk.
No kidding. No kidding, yes, you use the disk. Yeah, and the disk is slow compared to everything else. I mean, you can do an awful lot of Erlang during one disk write or read. So yeah, we'll end up with two things. This is just a brief overview of some parts of the system. How do you crash the beam? Well, I think the best way to learn how not to do something is to learn how to do it. Right? I'm not saying this is all the alternatives, but anyway, yeah. Fill the atom table. When you do the 1 millionth of one atom, try to create that, you crash the system. No way around that. Just do that. You can overflow the binary space. You're just creating and sending through so many big, large binaries, and they get taking so long time, relatively so long time to clean up. You just fill the binary space, or you just fill the memory and crash that. And there are applications that actually do that. Uncontrolled process heap growth. So what do I mean by that? The process heap grows, well, the heap for a process grows as necessary. So when it needs more space, it grows the process. More data in the process heap, more messages in the message queue, just keeps growing it. And eventually, the system there'll be no memory left for the system to take, and that crashes the system. Yes, there's a question.
Define what you call a very long message queue.
Large enough, a very long message queue, that was the question. A very long message queue is one long enough to crash the system. I can't give you a figure. I mean, it depends what's on the message queue, of course.
That seems
Yeah. A typical case where that can happen is you have a logger, and you're sending lots of logging information to the logger, and the logger is doing something smart like writing it to a disk or something like this, and it can't keep up with the messages, and the message queue slowly grows, and suddenly the whole system goes down. It does happen. Yeah. Infinite recursion is a good one. We don't check that. The system does not check that. It will happily recurse till death, right? And if you're just making a bigger stack, eventually you'll run out of memory and crash the system. And then you get some message, something saying you couldn't allocate, the process couldn't allocate something which was 100 megabig or something like that, just running out of space. You have a lot of data. Alexander was mentioning what they had, something with, how much was it? 170 meg of memory, no more, 17 gig of memory, I think. 16 or 17 gig of memory in one process. You don't need many of those to crash the system, right? What?
We have 32 gigs processors.
Yeah.
R14 can't handle that, but
If you want to talk big memory, talk to Eric. He's from Klarna, and they use a lot of memory for stuff. So yeah. NIFs. Errors in NIFs and LinkedIn port drivers. You reference 0 in a NIF and you crash the system. Crash the whole Erlang system, everything. Same thing in a LinkedIn driver. The system cannot protect itself against that. So, if you're doing things like NIFs or LinkedIn drivers, make sure you don't get errors in them. Especially if you're taking code from somewhere else, right? That can do it. Sometimes you can actually, I don't think they've fixed it now, but I think in R14 or early R15, you can crash the system by starting up the observer in the wrong way, or the rel tool in the wrong way. You can crash the system doing that. Because that was run internally in the system, and you got it to generate a memory reference error. You crash the system. Actually got a SIG bus, I think, on the Mac, which I haven't seen for about mid-80s. You can actually get a SIG bus. Well, there's always a segment violation. Anyway, yeah. So that's really, there's no way around that. So be careful, especially if you're using borrowed code or code from somewhere else. The alternative, of course, is to put in a port and run in a separate operating system process. Then if it crashes, it won't crash the Erlang system, but it's slower because you're literally sending data between operating system processes, but it's safe. Yes?
How many orders of magnitude slower?
The question was how many orders of magnitude slow. I have absolutely no idea. Again, it's like everything. What do you want to pay for? Right? If you want security of the system, then you put things in other operating system processes and pay the price in communication costs. If you want faster communication, you bake it in the system, but then you perhaps pay the price that you might crash the system. So I don't know. I haven't really done any serious tests for it. When we developed Erlang, we were quite paranoid about crashing the system, so we happily put everything outside. Yeah. That's me. I want to show one thing, both here in relation to the previous talk. Yeah, a lock example here. This is a small program. I will admit it's very pathological, but if you look here and look at the time it takes to run this application compared to the number of schedulers you're running, you find the more schedulers, actually the more cores you're using, the slower it was getting. Okay, and this was not inherently a sequential application. This was starting thousands of processes doing work. The more cores you had, the slower it went, which is something you wouldn't expect. And the data, you could look at the data, sorry, wrong way, that way. The other way around, here you can see the speed up as you increase the number of schedulers, and it's actually getting slower. So the more cores you had, the slower it was getting, which was not quite what you expect. And this is purely a synchronization bug, or synchronization fault, or problem. So it spawned a bunch of processes which was creating timestamps. So it spawned about 3,000 or 4,000 processes. They just created timestamps using Erlang :now and just comparing the value of them. And then after a while, they just send their reply back to the master saying, yeah, all the timestamps are growing, which is what they were testing. The problem was they were using Erlang :now. And Alan Kohler now has a wonderful property that it's always monotonically increasing. So for every call of now will be bigger than the previous one. So, for those who don't know, that returns the current time in microseconds. It's a tuple of 3 elements in microseconds. And it guarantees to increase. Which means if you're running on a multi-core, you have to have a centralized now there, and you have to synchronize and lock access to it so you can increase it and do it. And this, okay, this was pathological, but that's all they were doing with reading this. And the blocking caused by doing this synchronization made them go slower the more core you have. If you change that to do an operating system call into the timestamp, it went faster as expected. Right? So what I want to say here is synchronization does cost. So anything you can do to release it, lessen it, is actually a big win. And that often costs much more than you think. So yeah, that's about it. Wait. Sorry, no, picked one too many. That way. That's the way we go. Right, thank you. So, questions?
So if I want to spawn, 1,000, 10,000, 100,000 processes, there's nothing in the VM that will do that concurrently. It will do it serially, a single spawn at a time.
Well, the question is, can you spawn processes concurrently? Well, yes, you can spawn spawners.
Yeah, but you have to do that.
You have to do that yourself, yeah.
There's nothing in the VM that
No.
recognizes, like, I'm going to spawn a block of
No.
processes.
You spawn one process at a time. The spawn operation is synchronous. It returns when the process has started. So if you want to do concurrent spawning, then you spawn spawners like that and do that, yeah. Or start at the front and work backwards, yeah.
Why do the schedulers trade master rounds? Why is there not just one set master scheduler?
I don't, to be so honest, I'm not certain. I would guess that between this setting up in, when one wins, the master doesn't do anything. There's no reason, there is no master. I mean, apart from that, that's all it does, then it's just a schedule like anyone else, right? You couldn't suspend the master in that case. So, yeah. Yeah, next.
What was the sort of reasoning behind picking the exact values for the number of inductions at which you switch to master? You said 40K was the example.
Yeah. So the question was why we have these values for switching and stuff. 40K is because that's 20 times 2K. And 2K is the limit for a context switch within a process. And why that is 2K, well, it used to be 1K, and that was basically sort of a unit of time that was small enough to be not big. Right, put it this way. That was, okay, it was a reasonable value for rescheduling processes. That slowly grows. I think Kenneth said something like that 2K is probably too small now because it's so fast. So now you at the back and we'll move forward, yeah. No, well, okay.
What's the reason for not having a max process heap size function or response function?
I don't know. Honestly, I don't know. The general problem is, in general, the problem is that if something goes wrong somewhere with some process, grows too big or whatever, it can be very hard to work out which process is actually the error. So just because my process is the one that actually runs out of memory doesn't mean it's my fault, really. It might be some other process that's actually the fault, which I should be killing. So it can be hard to work out who's actually to blame, right? That was the original rationale behind it. Yeah. So you were first, then you. Yes.
It's a two-parter about big binaries. So first is when you're allocating a big binary and it overflows in binary heap size and crashes the beam, is there any way to catch that inside your process? No?
Nope.
That's a horrible thing. The second one, I think I read that your process size never shrinks. So if you have a process who is vacillating in size, should you just kill it and start another one?
It does shrink. The process heap shrinks.
Okay.
it recognises, I don't know the limits for it, but if it recognises after it's done a garbage collection and it's much smaller than it was before, it will shrink the size of the heap. But it won't shrink below this minimum heap size you've set. And there was one more than I have to go, so to speak.
How are the reductions calculated when you're making like a function call or something?
It's a function call. Every function calls one reduction. Yeah.
Okay.
And
It's just sort of calculated out.
yeah, it's kept in the process, just a counter. You can, when you're doing NIFs now, set reduction counts. So you can say, my NIF is doing 5 reductions, or the equivalent of 5 reductions or something, which you should actually do if it takes time.
Process info and check them.
Yeah, yeah. Anyway, now I have to stop. My time is up. So, thank you.